Okay, ladies and gentlemen, good day all. Today we are going to look at the quantum numbers. What are the quantum numbers? Quantum numbers are the numbers that are used to describe the distribution of electron density in an atom. Remember, we have electron configuration of an element. We have three ways of writing electron configuration of an element. We have shell configuration, we have orbitals configuration, as well as box configuration. So we use quantum numbers to know the position as well as the distribution of an electrons in an atom. So we have three quantum numbers that are necessary to describe an atomic orbital. We have principal quantum numbers, and the importance of principal quantum numbers is to designate, is to show the size of an electrons in an atom. And these principal quantum numbers is always represented with small letter n. Then we have angular moment quantum numbers, or in some other textbook you will see azimuthal quantum numbers or spin quantum number, azimuthal quantum number or subsidiary quantum number. So angular moment quantum number, subsidiary quantum number, as well as the azimuthal quantum number are all represent the same thing. So the angular moment quantum numbers is just trying to show the shape of an electrons. Then magnetic quantum number, which is represented with m subscript l, it specifies the orientation of an electrons. It gives the orientation of an electrons. So if you check some other textbook, apart from these three quantum numbers, there is also the fourth one, which is also we are going to discuss it here. We have also spin quantum number. And the importance of spin quantum numbers is just to show the direction of the electrons. So now we are going to look at the principal quantum numbers. As I said, it is represented with small letter n, and it gives the size of an orbital. So the larger value of n correspond to a larger orbital. So it means that the larger the value of n, the larger the orbitals. For example, if you have n is equal to 3, it means that in that atom you have 3 shell. You have 3 shell. If it is 1, it means you have only 1 shell. If it is 2, you have 2 shell. If it is 5, it means you have 5 shell. So the value of n corresponds to the value of n in Bohr's model of the hydrogen atoms. So it means that n is the same thing as the n in the Bohr's model of an atom. So a collection of an orbital with the same value of n is fundamentally called a principal energy level or shell. So remember, I told you n is like a shell, and if you have orbitals configuration, like where you have 1s2, 2s2, so the numbers that attach to that orbital is called energy level. So we also call it principal energy level. So it can be principal energy level or it can be shell. Like for example, in sodium, the atomic number of sodium is 11. So if you have sodium as 11, when you draw the electronic configuration as 1s2, 2s2, 2p6, 3s1, so you see in the s, the last s with 1 electrons as the index number, you have 3. So it means the 3 there is your principal quantum number, okay? And then the next thing is the angular moment quantum numbers. As I said, is describe the shape of the orbital. So the values of L are integers that depend on the value of the principal quantum number. So for example, if you have, let's say, there is also a formula that is used to get the value of L. And this formula is n minus 1. So if you have L is equal to n minus 1 and you have n is equal to 2, so it means that for you can easily get your value of L. So therefore, now it is just easier to get this. So now the next thing is, it's now, just now look at it. If we have L is equal to n minus 1 as a formula, then for you to get the value of L if n is equal to 2, you just apply the formula. And how do you apply the formula? It's just by simply saying L is equal to 2 minus 1. So 2 minus 1 is equal to 1. So it means that we have the value of L is equal to 1. Then we now take this one here, and just say also L is equal to this 1 minus the 1 from the formula here. So we have 0. So it means that if we have n is equal to 2, we have two possible values of L. So look at it now. These are the two possible values, 1 and 0. So therefore here, whenever you have L is equal to 0, it means you have s orbital. And whenever you have L is equal to 1, you have p orbital. And whenever you have L is equal to 2, then you have d orbital. And whenever you have F is equal to 2, sorry, whenever you have L is equal to 3, it means you have F orbital. So this is very, very important. So whenever you are actually trying to do some electronic distribution, it is very, very important to know the position as well as the location of the electrons. Okay, so this is this. So principal quantum numbers, it gives the shape of the orbital, and then it's from there. Remember that from basic chemistry, p or s orbitals is always spherical in shape. Then p orbitals is dumbbell, d orbitals is double dumbbell, while f orbitals is very, very complex, so it's not determined. Okay, then now we are now moving to the next, and then okay, so now the next thing is the principal quantum number. The principal quantum number. So in the in the magnetic quantum number, the next thing is magnetic quantum number. So the magnetic quantum number is just trying to give the orientation of the orbital in space. So it's very important here. The value of m are integers that depend on the value of the azimuthal quantum number, which is the angular momentum quantum number. So that is why the value of m is range from, that is the magnetic quantum number. The value of magnetic quantum number range from minus L, 0, and plus L. So when n is 1, so L can only be 0. It can only be 0. And then when L is 0, then of course L, when L is 0, then M, which is the magnetic quantum number, is only 0. And then when n is 2, remember I told you L is equal to n minus 1. So you can have 0 or 1. So if it is 0, it means you have only 1. So you have only 0. Then if L, if n is 2, as we said, it can be 0 or 1. So it means that L can be 0 or 1. So if L is 1, it means that you have a possible value of minus 1, 0, or plus 1. So remember I told you whenever you have L equals to 1, you have p orbital. So this is the reason why if you come for the box configuration, if you are writing the electronic configuration of an element using box configuration, you will observe that p orbital have 3 orientation. It has 3 orientation, and it's because of this minus 1, 0, plus 1. It means The first orientation is -1. This one is 0, the second box. And then the last one is +1. That is why we have px, we have px, we have py, and then we have pz. This is why we have 3 subshell in p orbital. And then when n is 3, remember from the formula, L is equal to n minus 1. So now it can be, since n is 3, then it can be now 3 minus 1, then is equal to 2. And then you now take this 2 and say 2 minus 1. Then you also have 1. And then you now take this 1 minus 1. Then we have 0. And this is the reason why when n is 3, then you have 3 possible values of L. So you have 0, 1, or 2. So when L is 0, then you have only 0 here as M. Then we have 1, you have -1, 0, or +1. And when you have 2, you have -2, -1, 0, +1, or +2. That is why in d orbital you have 5 boxes. The first one is -2, -1, 0, +1, and +2. So let's stop here for this one and we will continue.